3 iDEN radio production lines have been deployed in record time at the land mobile product sector in Plantation, Florida. This effort was made possible by the collaboration of LMPS and MMS teams. The iDEN production lines were designed with various key objectives. They included increased throughput, improved product quality, reduction in manufacturing costs, flexibility to accommodate new product introductions, reuse of available test equipment, and rapid deployment. These objectives require the implementation of new equipment and manufacturing processes such as gang placement, faster and more accurate chip shooters, online PCB inspection, board test audit, and automated back-end testing. The back-end test area proved to be the most challenging as a large number of test fixtures had to be accommodated in a very compact area. LMPS and MMS form cross-functional teams encompassing mechanical and electrical design, software, assembly, tooling, testing, and maintenance disciplines. Weekly interaction between the teams accentuated our priorities in reuse and rapid line deployment. The iDEN Integrated Digital Enhanced Network Radio is a multi-service digital communications device. The product features full duplex interconnect, similar to cellular, plus private dispatch, paging, messaging, and data fax communications. The iDEN radio is now in use throughout the United States, Canada, South America, Japan, and Europe. The iDEN radio production line consists of an automated front end, a manual radio assembly area, and an automated back-end radio test area. This line can process a variety of iDEN radio models and is capable of producing up to 180 units per hour. The line begins with a board loader, which delivers printed circuit boards to the screen printer. The screen printer is MPM's newest high-E automatic screen printer, featuring increased accuracy and throughput. After printing, boards are transferred to a Nitto gang placer, which places 20 by 40 and 30 by 60 components from bulk cartridges. The gang placer capability to place 400 components in 16 seconds is a key element in achieving the desired line velocity. Small component placement continues with the Sanyo TCM 3000 chip shooter, capable of placing 36,000 parts per hour. This chip shooter uses direct drive head technology and has a moving part count that is 40% less than traditional chip shooters, thus increasing placement, accuracy, and reliability. Boards are then transferred to a universal GSM2 fine pitch mounter. This machine places large integrated circuit devices and odd-shaped parts using state-of-the-art component vision technology with 6 sigma accuracy. The GSM2's versatility allows for complete automated placement of all iDEN board components, thus eliminating the need for any manual placement. Populated boards are inspected prior to reflow with a GS1 vision inspection machine, which can verify component presence, accuracy, and polarity. The GS1 allows operators to repair defects online before reflow, and most significantly, it contributes to reducing the need for 100% board-level testing. After inspection, boards are transferred to a second GSM2 fine pitch mounter, which places the RF shields. Once the first side of the board is populated, it is transferred to a BTU VIP98 reflow oven. The VIP98 uses forced convection reflow technology and is continuously monitored for heating, cooling, and belt speed accuracy. Reflow boards are transferred into a first-in, first-out buffer, which is designed to cool the boards before second side screen printing. The board is then rotated for second side population. The equipment used to populate the second side is nearly identical to that just described. 2 board test fixtures are used to test the boards on an audit basis. The audit was designed to limit possible exposure to manufacturing defects and thus reduce scrap. A palletized conveyor system is used for all manual assembly operations. The assembly functions are designed in groups of 4-cycle independent stations, each capable of manual bypass during operator absence. The conveyor system has an empty pallet return, which is located below the product lane. The pallet conveyor system is integrated into the first back-end test station, which robotically transfers the radio from the pallet to the belt conveyor used in the back-end test area. In automating the back-end radio test, every effort was made to reuse existing design test fixtures and electronics. The objective was to minimize development cost and to ensure accelerated deployment. Close interaction with the Motorola Manufacturing Systems Automation team was key in facilitating information transfer and project coordination. Each of the 5 test stations uses a simple controller to control robotic motion, product transport, radio identification, and correlation checks. The station controller is in active communication with the test controllers, which command the actual radio tests. The test controllers retrieve radio specification and test profile files from the server, and once a test is completed, they send the test report to the server for quality control record. Each test station is capable of operating in automatic, manual, and bypass mode. Switching from one mode to another is accomplished via a simple user-friendly control panel. The manual mode allows manual production to continue during service of any of the stations. The 3-lane belt conveyor separates radios that have been successfully tested from those yet to be tested and those that have failed. The reject conveyor returns the defective radios to a technician for further manual diagnostics and repair. Once repaired, the radio is reintroduced to the line for retesting. The Customer Interface Test, CIT station, performs tests on the radio keypad, display, speaker, earpiece, and ringer. This station contains 4 independent pallet drives which advance and locate the test nest into the test position. Once the test nest is located, the test head is activated under a programmed routine, while downward-looking cameras inspect the radio display for missing icons and pixels. Keypad type and backlighting tests are also performed at this station. The test heads are customized for each radio model and have been designed to be easily removable. Each of the 3 inline RF tune and test stations accommodates up to 8 test boxes. Product transport is simplified by the use of a single-axis belt-type actuator and a pneumatic end effector. The robotic end effector retrieves the radio from the conveyor, identifies it, and proceeds to place it in the first available test fixture. Once the tuning process is completed, the radio is returned to the transport conveyor for further processing. A calibration radio is present at all times in each test cell for periodic checks. Floor space utilization was optimized in the test area by locating the test racks on top of the tune and test stations. After tuning and testing is completed, the antenna is manually inserted and the radio is transported to the air test station. In the station, the capability of a radio to communicate is verified. After passing verification, the radio is ready for packaging. The new iDen radio production lines were deployed in record time. Overall product quality has been increased to 5.65 sigma, and cost per unit has been reduced significantly compared to earlier iDen production lines. The automation of the back-end radio test has reduced the number of operators in the line by over 30 associates during a 3-shift schedule. Plans to automate radio testing in older manufacturing lines are being explored.